Hello friends, this is 2nd of April and now the complete lockdown has been laid over the world, India and in the Maharashtra. It looks like the complete world has stopped. Our India has stopped, our Maharashtra has stopped. But though the country has stopped, though the world has stopped, our studies should not be stopped. So for the same purpose, I have brought the another topic of pharmacology for our study and is nothing but the dose response curve. So it is going to be one of the simple and easiest topic, dose response curve. So whenever you have to measure the effect of a particular drug in the form of its response, you can record by using the dose response curve. What should be called a dose response curve? So it is a simple one, the graph obtained by plotting the dose on x-axis and percent response on y-axis. So with the increase in the dose, definitely the responses are going to be vary, so that should be collected. The responses at a different doses should be collected and dose should be taken on the x-axis, that is abscissa, and percent response on y-axis. So whenever you plot such a graph, and this graph is known as a dose response curve. The purpose of plotting the dose response curve is very clear, and there is nothing but what it is used to measure the effect of drug. So if you want to measure the effect of a drug, whether it is effective or not, what is the potency of that drug, it can be well studied by using dose response curve. Many things are there that can be obtained by using the dose response curve, that could be considered as the application of dose response curve. Throughout this presentation we will come across the uses of a dose response curve or the applications of dose response curve. So stay with me in the next part of the presentation. So whenever we set the dose response curve, we can say that there are two types of dose response curve, graded dose response curve and controlled dose response curve. When you are going to study the responses within a single animal, single tissue, or single individual, at that time you can use the graded dose response curve. But when the variation with respect to doses has to be studied in the large number of population, at that time you will get the controlled dose response curve. In case of the graded dose response curve, the dose, whatever it is taken on the x-axis, serve as independent variable, percent response on y-axis serve as a dependent variable, and the tissue serve as a constant variable. Means tissue throughout the experiment should be constant. It should not be there throughout the experiment. You are not allowed to change the tissue. If you are going to change the tissue, you have to repeat the whole experiment. That's why tissue is considered as a constant variable. It should not be changed throughout the experiment. And the percent response is said as a dependent variable because it is going to change with respect to the amount of drug that is administered. So means what, it is dependent over the dose. What exactly the amount of dose is administered, it will definitely determine the magnitude of response. So it is dependent over the somewhere, that is nothing but what, it is dependent on the dose. That's why it is said the dependent, and the dose is an independent one, means we will determine what amount of dose should be administered, so it is said independent. So how the things vary in case of control dose response curve? So yes, it is here also dose serve as an independent variable, but there is a change in the dependent variable. Dependent variable means what, the number of animals responding, to a particular dose will be considered as the dependent variable, while what is a constant variable, the predetermined the response in case of the control dose response curve is predetermined. Means what, you can say whether the animal is dead or alive at that particular dose. It is a predetermined ones, means you know very well the animal is either going to survive or the die. So that is nothing but predetermined response. Sometimes the predetermined response will be like this, whether there is an increase in the 25% heart rate or blood pressure, so it is a predetermined. So constant variable is a predetermined response in case of control dose response curve. And here it is said the all or none, means in case of control dose response curve, you cannot say the animal, when the predetermined response is a death of an animal, you can't say whether the animal is 10% dead, 20% dead, and now it is 100% dead. It is dead or alive, so it is said all or none. Whether there are increase in 25% of heart rate, yes or no, so it is said that is the reason for what control dose response curve is said all or none effect. We should have the example. In case of the graded dose response curve, the example is a contraction of smooth muscle. When you administer the varying amount of dose to a smooth muscle, so how the contraction is going to be vary. If you study, that is an example of graded dose response curve. And if you study acute toxicity studies in animal, means if you are going to find out the lethal dose, if you are going to find out the lethal dose which is considered as a fatal to the animal, so that kind of study should be involved as a control dose response curve. So how will you plot the dose response curve? So we will definitely speak about the graded dose response curve. Our focus will not be towards the quantal dose response curve. As far as this presentation is considered, we will limit our discussion towards the graded dose response curve. So first of all, what you have to do, you have to collect a fresh tissue. It may be either intestine, it may be a trachea. So intestine of hen, intestine of goat can be collected from the slaughterhouse. Suppose it looks like this one, the rectangle size. And as soon as you collect this tissue from the slaughterhouse, it should be kept into a suitable container. It is said the organ tube, and this organ tube should be previously filled with the physiological salt solution. And now the tissue is placed into organ tube which is previously filled with the physiological salt solution. The experimental setup is quite different, but that is not the scope of our presentation, so I am not going to explain what exactly the practical setup you require to carry out this practical. Somewhere whenever I will get the enough time, at that time I will prepare a separate video over that one and post over the YouTube. So now we are having the tissue. Tissue is placed into the organ tube. Organ tube is previously filled with the physiological solution. Now the tissue is in contact with the physiological salt solution. Now we will administer a smallest dose of a drug, and this time it is acetylcholine. So we will start with a very small dose of acetylcholine. It is 0.1 ml. So now I have to fix the first of all the concentration of acetylcholine. It may be 10 microgram per ml, 100 microgram per ml, or 1000 microgram per ml. Suppose we have taken the acetylcholine of concentration 10 microgram per ml, and now we have introduced the 0.1 ml of 10 microgram per ml of acetylcholine to the tissue like this. Whenever the drug is administered, definitely it will produce the effect by acting over its receptor. So what will happen? We have to record its response, and suppose if a 0.1 ml of a drug is administered to the physiological salt solution, the drug act on the receptor and it will produce the contraction. Definitely acetylcholine produces the smooth muscle contraction, so it produces the 1 centimeter of contraction. It can be recorded just like this. So first of all you need to record the baseline. Baseline means what? It should be recorded before the administration of drug, and once you administer a drug, the recording will be like this. So 1 centimeter of contraction can be recorded with the upright movement of writing point. So this is nothing but what? The 1 centimeter of response. We should carry next practical, carry the practical to the next. So this time we will add the next dose, and this next dose should be double to the previous dose. So previously we introduced the 0.1 ml, now we will introduce 0.2 ml, and again after introducing 0.2 ml we will record its response. And now suppose the kind of response, the magnitude of response produced, it is 2 centimeter, then we will get the recording just like this. For 0.1 ml you will get 1 centimeter, which one introduced previously, and now we introduce 0.2 ml, now it will produce 2 centimeter of response. We have to repeat the similar manner. We have to repeat the similar manner for the higher doses. Higher doses of acetylcholine is introduced, and again their responses are recorded. For example, when 0.4 ml introduced, 4 centimeter response we got. 0.8 ml 8 centimeter, 1.6 ml 10 centimeter, 3 ml, and we will get the recording just like this. So whatever this recording, so 0.1 ml introduced 1 centimeter, 0.2 ml produce 2 centimeter, 0.4 ml 4 centimeter, 8 centimeter, 10 centimeter, 10 centimeter. It is this recording is only kind of example. I will not suggest that whenever the 0.1 ml of drug is introduced, it will produce always 1 centimeter. It is only for the sake of our understanding. I have said that 0.1 ml produce 1 centimeter. These responses, the magnitude of responses may vary depending upon the sensitivity of that tissue or ileum. It is going to be vary. So whatever this recording you will get, the recording of responses, this is known as a chymogram. So most of the students get confused. They used to call it as a dose response curve, and whenever the external examiner asks him to show the dose response curve, they show this chymogram to the examiner, and says that this is a dose response curve, but this is wrong. This is a chymogram. It should be called as chymogram. And by using chymograph, it is recorded. Chymograph means what? Your Sherrington rotary drum like instrument are known as a chymograph, and the recordings are known as a chymogram. So now we are having the dose and recording of their subsequent responses in the form of chymogram. So now what will we do? How to obtain the dose response curve? So you need to take the graph paper and take these doses on the y-axis, sorry, these doses on the x-axis, and the percent response on the y-axis. So this maximum response should be considered as 100%, this one 100%. With respect to that, for 8 centimeter, for 4 centimeter, 2 centimeter, it should be calculated. So if a 10 centimeter is considered as 100%, 8 centimeter should be 80%, 4 centimeter 40%, 2 centimeter 20%, and 1 centimeter 10%. So when you plot a graph of dose versus percent response, so whatever the graph you will get, it is now should be called dose response curve. But what is this one? We observe that whenever we administer 1.6 ml of dose of acetylcholine, it has produced 10 centimeter response. But when we increase the dose, there is no further increase in the response. If you still increase the dose, means the next dose is administered, suppose it is 6.4 ml, but it will not produce any increase in the dose, so it will be again 10 centimeter. So 10 centimeter of the response should be considered as a maximum response. So what is a maximum response? And this maximum response is known as a ceiling response. So it is a response. How will you define the ceiling response? It is a maximum response beyond which the increase in the dose should not increase further magnitude of a response, known as a ceiling response. It is a response at which further increase in the dosage should not produce any increase in the magnitude of response. So this is ceiling response. So in this example, 10 centimeter is considered as a ceiling response, and the dose which produces the ceiling response is known as a ceiling dose. So in this case, 1.6 ml of 10 microgram per ml of acetylcholine should be considered as a ceiling dose. So if you plot a graph, so this is nothing but what? If I take the dose on x-axis and percent response on y-axis, I will get a graph, and this time I will get a hyperbolic graph. This is known as a dose response curve. So what is this one? You can find out the ceiling response. Ceiling response means maximum response. It will provide you the idea about the efficacy of a drug. And the subsequent dose that produces ceiling response, it is known as a ceiling dose. But now if you get such a hyperbolic graph, it is having certain limitations. It is difficult to distinguish the responses of a drug at smaller adjacent doses. The first smaller adjacent doses, there is a little difference between the responses, very small difference, and it is difficult to distinguish whenever we plot the dose response curve. Then you may require the wider graph paper if you know the higher doses. Means our this practical restricted to as a 1.6 3.2 ml, but sometimes you may require the higher doses. So at the time you may require the wider graph. So these limitations can be overcome by taking the log dose instead of dose on x-axis. x-axis पे अभी हम dose नहीं लेंगे, तो उसके अलावा लेंगे log dose. So the graph obtained was log dose versus the percent response. Now it is known as a log dose response curve, and you will get the graph just like this, which is a sigmoid shape or the S shape in structure. So log dose is taken on the x-axis and percent response is taken on the y-axis. So now it is known as a log dose response curve instead of saying the dose response, and it helps to overcome the certain limitations. So with the help of this log dose response curve, what are the applications? You can easily find out the ED50, means it is the dose required to produce 50% of a maximum response. So here, by extrapolating the 50% of response towards the x-axis, towards the dose, you can find out the dose which is required to produce the 50% of effective response. You can find out the efficacy of a particular drug means this drug is considered as 100% effective. You can compare this one with any other drug and find out its efficacy. You can also find out its potency, means the amount of drug required to produce the desired pharmacological effect can be well studied. Means the potency of two drugs can be also compared by using the dose response curve or the log dose response curve. So you can find out the LD50, you can find out the ED50. So in case of the single individual, you can find out the LD50. It would be the application of quantal dose response curve, but here you can find out the ED50, you can find out efficacy, you can also find out the potency, means the minimum dose required to produce the desired therapeutic effect can be find out with the help of log dose response curve. So now we should study with the help of dose response curve competitive antagonism. This is all the observation table we have prepared when the acetylcholine is given. When acetylcholine is given in 0.1 ml, 0.2 ml, 0.4, 1.6, 3.2, 6.4 like this, you got the 100% of response because it has produced the maximum response of 10% here, and we have calculated the percent response for the subsequent doses. We also find out the log dose values for the subsequent doses. So log of 6.4 is almost 0.8, log of 3.2 almost 0.5, and likewise that. And we are also having the similar experiment. Repeat the similar experiment in case of in presence of the competitive antagonism, in presence of competitive antagonist of acetylcholine, and definitely it is a atropine. So similar experiment we are going to repeat in presence of atropine. This time we will always administer the acetylcholine along with, always, every time whenever we are going to administer the dose of acetylcholine, every time we need to administer the atropine of 0.2 ml of desired concentration. The concentration may vary. Here I have taken 10 microgram per ml. So every time along with the acetylcholine of 0.1 ml, 0.2 ml, 0.4, 0.8, 1.6, 3.2, every time you should administer along with 0.2 ml. Now what will happen? Your observations are going to be changed. Initially when you introduce 0.1 ml of acetylcholine, it has produced 1 centimeter of response, but now it will not produce 1 centimeter of response. Definitely it will produce a response less than that. So coming here, so I have given the example that it has produced the 0.5. So always it may not be the half of that one. It may vary. Sometimes it may be 0.6, 0.7, 0.8, but I have taken an example 0.5. So somewhere initially it has produced 10% of response, now it has produced 5%. And likewise I will find that when acetylcholine is given alone, it has produced a higher response in presence of atropine. Here 40%, 20%, 80%, 40%. When 1.6 ml of acetylcholine was introduced alone, it has produced the ceiling response. But now, when in presence of atropine, it doesn't produce the ceiling response. So still it required to take the higher dose. So when 3.2 ml of acetylcholine is given along with 0.2 ml of 10 microgram per ml, now it has produced the ceiling response. So ceiling response. So this is nothing but what? The similar. In order to obtain the similar response, 10 centimeter of response, how much of the drug is required? Acetylcholine alone, if given alone, require 1.6 ml, but when it is given in presence of atropine, it require the next dose, that is higher dose, 3.2 ml. So in presence of atropine, the ceiling dose of acetylcholine is 3.2 ml, and in absence of atropine, the ceiling dose of acetylcholine is 1.6 ml of 10 microgram per ml. And if we plot the log dose response curve of both acetylcholine as well as acetylcholine plus atropine, we will get like this. So this is nothing but what? The shift in the dose response curve of acetylcholine, shift in the dose response curve of acetylcholine in presence of atropine, that is competitive antagonism. This is an example of competitive antagonism, and here you will find that the dose response curve of acetylcholine in presence of atropine gets shifted towards the right hand side. So here it is the shift in the right hand side. Does it affect the efficacy? Definitely atropine at the efficacy of acetylcholine in presence of atropine doesn't affect the efficacy, because of what? When acetylcholine is given alone, it has produced 100% of response, and when it is given along with the atropine, it produces the 100% of response, but definitely it affects the potency. So in case of the competitive antagonism, In case of the competitive antagonism, the efficacy of a drug doesn't get changed. Efficacy doesn't get changed. So what affects? It affects the potency. Initially, it required 1.6 ml to produce the maximum response, but in presence of atropine, it required to administer the higher dose, that is 3.2 ml. So in absence of atropine, acetylcholine is much more potent, but in presence of atropine it is less potent. So potency is affected while the efficacy is not affected. It is an example of competitive antagonism. I said the competitive antagonism, but when the non-competitive antagonists are given, definitely it will affect the efficacy. It will affect the efficacy as well as the potency. So that's all about our discussion related to the dose response curve. If